Yes, good morning all the students. How did you fare in your exams? How is the paper, machine learning paper?
Good, ma'am.
Good, very good. Let me see in your answer sheets how well you did. Okay. Can you see the presentation? Right.
Yes, ma'am.
Okay, before our exams, we started this decision tree learning chapter, and we have covered two concepts in this, that is decision tree representation, how we use a decision tree in order to represent the training examples that have been encountered, and appropriate problems for decision tree learning. Okay, so how we understood to represent a decision tree, we'll take a root node and we give a condition in this root node. Say the customer is married. Yes, then check another condition. Say his income is greater than 10,000. Then yes, okay, he is not a defaulter of the loan. No, then he may be a defaulter of the loan based on the training examples. Remember, a decision tree is constructed based on the training examples provided to it. Means a decision tree is trying to learn from the training examples that it has encountered for this combination, for this value of an attribute. If it is S, then further what has to be checked in order to predict a label, target label. If it is satisfied with that present attribute's value itself, then it can directly predict the label. Say if the customer is married, yes, then immediately for all the training examples, when the customer is married, then he paid the loan. In that case, no further checking need to be given, right? So for that particular attribute, it is classifying. If it is yes, need not check any other attribute. If it is yes, it is classifying it as true only. And say the customer has paid the loan itself, right? But if it is no, then some other condition have to be checked, right? We'll see with an example how this is exactly being done. So the decision tree is constructed by using a root node which best splits the training examples into positive and negative examples, means which can better classify the training examples. Now, once that condition is true, it branches to yes or no further conditions. Then it takes another attribute there in the subtree and again builds another subtree there based on yes or no conditions, or based on the attribute values. Always it may not be yes or no. It may be sometimes, say his income level is greater than 10,000, less than 10,000, and greater than 50,000. Like that, there may be some range of income. In that case, we may have to check multiple conditions, right? So whenever attribute is checked, that is checked at the root of a tree. Now, when a further condition is checked, it is again the root of a subtree here, not a root of the entire tree, but a subtree. Now, this subtree can further branch into different conditions. Again, conditions may be checked, or it may reach the leaf node. Why? Because the classification task has been completed. Means for that particular path of attribute values, it always classifies it as a positive example or a negative example. If there is a confirmation of that, immediately you can attach a leaf node. But if there is no confirmation, further you have to check the attributes. In that case, you have to start with another root node for a subtree, right? That is how a decision tree is constructed. Now, we have also seen appropriate problems for decision tree learning. When the data is noisy, when the data has missing values, when the data has some outliers, or when the training examples are the attribute values are represented in the form of key value pairs, like attribute, say humidity is equal to high, or humidity is equal to low. means a key and a value, attribute and a value. If that kind of pair, if data can be represented in that format, then we can go for opting this decision tree algorithm. And also it supports both disjunctive and conjunctive rules. Disjunctive means or. If this is not correct, or if this is correct, or this is correct, or this is correct, that kind of checking can be, condition checking can be done by decision tree algorithms. And it can also use if this is true and this is true and this is true. This is called as conjunctive form of rules. Even that can be applied by using decision trees. In previous chapters, we have learned about finders algorithm and candidate elimination algorithm. For those two algorithms, they support only conjunctive rules. They doesn't support disjunctive rules. But that problem is overcome by using this decision tree representation, where they even support disjunctive rules. Right? Now, if you take a root node and go along with this, we can treat it as a and rule, right? If this is true and this is true and this is true, it goes on like this. Along the path of tree from root node to the leaf node, it is an and rule or conjunctive rule. But if you take like this, a root node, this or this, in this case, this is called as disjunctive rule, because we go with S or no, or married or not, male or female, right? There we are having a disjunction between the attribute values. We can either consider this value or this value. In that case, this value is okay, or this value is also okay. In that case, we can go for disjunctive rules. For this kind of problems, you can opt for decision trees. So when the data set is noisy, when the training examples are having noise and outliers, and when the training examples want to include even the disjunctive hypothesis, and whenever you have the attribute values in the form of key value pairs, in such cases, you can select this decision tree learning. Okay, you are able to recollect what we have done in the previous session by this introduction. Okay, now let us proceed with today's concepts, the basic decision tree learning algorithm. In that, which attribute is the best classifier? How to determine which attribute is the best classifier, which can classify the training examples without any impurity. Perform the classification in its pure form. Right, I'll tell you what it is, impure and pure. Okay, which attribute is the best classifier? By using entropy measures homogeneity of examples, and information gain measures the and also another topic, information gain measures the expected reduction in entropy, how it measures the expected reduction in entropy. Okay, by covering these two concepts, we'll understand which attribute can be selected as the best classifier, right? And in next session, we'll see that with an illustrative example. So just pay attention for today's concept. It is somewhat theoretical and with some examples still. And if at all you are having any doubt in this, it can be understood in your next session by going through a very clear example, right? Now, the basic decision tree algorithm, let us see how they actually work. What is the basic idea followed by the most fundamental decision tree algorithms? Most algorithms that have been developed for learning decision trees are variations on a core algorithm that employs top-down approach and greedy search through the space of possible decision trees, right? Now, when you take your previous chapter, what are in the hypothesis space? You have various hypotheses, right? The hypotheses which are consistent with the training examples you have in the hypothesis space. Now, what is the hypothesis space for a decision tree? Do you have statements or do you have rules? No, you have decision trees itself. The hypothesis space for the decision tree learning is the decision tree itself. The tree that is learned from the training examples, the tree that is consistent with the training examples, the tree that represent each and every training example provided to it. Okay, so for this, in order to learn the decision trees, what approach is followed by the machine? It employs top-down approach from top, right from root node towards the leaf nodes. It tries to classify all the training examples, and greedy search. It will try to find out the best solution and also all the alternative solutions. Right? It tries to search the hypothesis space in a greedy manner. Right? It tries to cover all possible alternatives that may exist. Okay, that is called as greedy search. What are the fundamental algorithms that come under this decision tree learning? ID3 and C4.5. Now they learn decision trees by constructing them top down. We call this as top down, right? It starts with the root node, branches to the leaf nodes, and that leaf node again can be a subtree, or it can be the final leaf node. If it is a subtree, again it may extend to another level. But if it is the root node, then it can classify that particular training example clearly, right? This is how the decision tree is constructed in a top-down approach, beginning with the question. How it begins? What is the question that is put to the decision tree at the beginning, at the root node? Which attribute have to be tested at the root of the tree? Which attribute better classifies all the training examples? Which attribute will make the classification very pure? Right? That should be given at the root node so that the decision tree is optimal. It need not waste constructing a complex tree. See, if no proper attribute in this stage is selected, then the resulting tree may extend to many levels because it is considering every possible alternative for the attribute value. But if a proper decision is taken at this root node so that half of the training examples are classified correctly, then this and this will take up other part of the classification, so that you will result in a simpler decision tree that can be applied for that training examples. So what I'm trying to tell you is, if a better selection of attribute is made at the root node, then the tree complexity can be reduced. If vague selection happens for the root node of a decision tree, then the decision tree may result in being very complex decision tree with lots of subtrees and lots of levels, right? So the main idea to build a decision tree is which attribute to select at each node, which attribute to select at the root node, which attribute to select at the subtrees root nodes, in order to make a better classification and keep the decision tree as simple as possible. Okay. Now a descendant of the root node is created for each possible value of this attribute, and the training examples are sorted to the appropriate descendant node. What do we mean by this? Say an attribute is checked at the root node. Now a descendant of the root node is then created for each possible value of this attribute. Say here the attribute is sky. Now the sky is sunny. That is one possible value. The sky is cloudy. That is another possible value. The sky is, or it is raining on that particular day. Then that is one possible value, right? So a descendant is constructed or created for each possible value of the attribute selected at the root node. Here the attribute we have selected is the sky condition, and you have three possible values for that sky attribute. That is why it is branching into three different trees. Okay, now it is next attribute's value that determines whether the tree can be extended or that itself can be the leaf node. Okay, now the entire process is then repeated using the training examples. Again, for this, what you will do? Again, the process will be repeated. It checks another attribute and further the tree is constructed. Now, the entire process is then repeated using the training examples associated with each descendant node to select the best attribute to test at that point in the tree. Okay, now sky is cloudy. Let us take this branch. Now, when the sky is cloudy, if all the training examples are yes, in that case, you can simply make it as the leaf node and give it as S. But when the sky is rainy, still some other attribute values varied. Okay, no, there is a no. In that case, what happens? You have to check further conditions. Okay, the sky is rainy. Now, when the sky is rainy, other attribute also values also matter here. So you have to take the humidity. Another condition, if the humidity is low and if the humidity is high. In this case, if the sky is rainy and the humidity is high, the game is not played. No. In all the training examples, if the sky is rainy and the humidity is high, the game is not played. It's a no. So directly that will become the leaf node. Now, if the sky is rainy and the humidity is low, then further combination of attributes are existing. In that case, you have to check that. If the forecast is again what? Same, or it is changed. In that case, what will be the leaf node? Like that, it keeps on extending. At each root node of a tree or a subtree, a condition is checked, and based on the condition, if the classification is pure, it is okay. If the classification is impure, then it has to further check other conditions for the attributes. Okay. Now, this forms a greedy search for an acceptable decision tree in which the algorithm never backtracks to reconsider earlier choices. This is the only drawback of the decision trees. They can't backtrack. They can't go. Once an attribute is selected as the best classifier for that particular point, and it goes forward to construct further levels of the decision tree. Once the decision tree is constructed, it doesn't backtrack to check whether its previous considerations are correct or not. That is the only drawback. That is why we call it as greedy search and hill climbing approach. It is just checking its local best and going forward. It is not checking the global best. If it has to check the global best, it has to backtrack and iteratively change its attributes. But it is not iteratively changing its attribute. Once it constructs a decision tree, that's all. That is the final decision tree. There is no backtracking available. It doesn't check whether its local best attributes are even the global best attributes. In that case, what will happen? That is called as greedy search, right? It doesn't reiterate, it doesn't iteratively modify its learning. Okay. Now let us see the summary of ID3 algorithm. Let us have a quick look at it first by going through each and every step. And once you trace with an example, you will understand what all concepts have been discussed in each and every step of this algorithm. Okay, so what is the input for this ID3 algorithm? The training examples, the target attribute, and the attribute values. Means what? You remember, right? Say sunny is one attribute. Sky is one attribute. Humidity is one attribute. For these attributes, you have day 1 data, day 2 data, day 3 data, right? And you have a target value, whether it is whether they have played a game on a particular day given the weather conditions. Okay, these are called the target examples. Now, this D1, D2, D3 are called as training examples. This sky and humidity are called as attributes, and this final column target is called as the target attribute or the target label for that training example. Okay, now the machine tries to learn from this data, and whenever a new data point is given, on this day the sky is cloudy and the humidity is very high, then the decision tree will be used by the machine in order to predict whether the game will be played on that day or not. A tennis game or a cricket game will be played on that day or not. That will be predicted. Okay, this is how a decision tree is constructed. Okay, now let us see in detail how ID3 algorithm takes various steps in order to construct the decision tree. So what is the input? We have seen here the input is the training examples, the target attribute, yes or no, and attributes or the features, these sky and humidity. The features or properties are simply the columns. Okay. Now examples are the training examples. Target attribute is the attribute whose value is to be predicted by the tree. Okay. So what should be the prediction? Yes or no? Given the day's weather conditions, whether the game will be played or not, yes or no. Those are the target attributes. Now, attribute is a list of other attributes that may be tested by the learned decision tree. So these are the attributes which will be tested by the learned decision tree. Learned decision tree means now a decision tree has been constructed from the training examples. Now, if a new data point is given, it will test all those attribute values and predict what is the final outcome. Okay. Now, it returns a decision tree. What is the output of this algorithm? It returns a decision tree that correctly classifies the given example or given new data point or given a future data point. Okay. So, understand what is the input for this? The machine has to learn from the training examples, right? So the input is the training examples and their labels and the attribute values. And what will be the output? The learned decision tree, the tree that can apply to all these training examples. Now, how to start with? Initially, create a root node for the tree. Okay, a root node is created. Now, at this root node, what has to be done? If all examples are positive, you need not classify anything, right? All belong to the same class. In that case, you need not classify anything. Return the single node tree root with label plus, because all values belong to the positive class. In the same way, if all examples are negative, all examples belong to one single class, that is no, or a negative example, or 0, or whatever you take, default of the loan or not, no. All these negative examples, if it contains all negative examples only, then also you need not construct a decision tree, because all the training examples belong to only one class. Now, how can it learn further? It can't learn anything, right? All the examples, whatever are the combination of the attributes given, they belong to a single class. Then the machine can't construct any decision tree. In that case, it has to stop with the root node itself. It has to stop here itself. Okay, that is why if all examples are negative, return the single node tree root with label minus, or if they are positive, return the root node with plus. Okay, now if attributes is empty, if no attributes are given in the training examples, then what has to be done? Return the single tree root with label most common value of the target attribute in example. Say this is one extreme condition where you have all the day's data without any weather conditions. You have the target label yes, 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 no. These are the target labels. Now, if this attributes x1, x2, the columns, if these values are empty, then what has to be done? Return the single tree root, return the root again with label. What should be the label now? Most common value of the target attribute. What is the most common value here, students? Which is repeated more in the target label here? Yes or no? Which is repeated? Which is the most common value for the target attribute? Speak out. Are you there or taking rest after writing the exam? Simply logging in. Students, what is the most common value in this set?
Yes, yes.
Yes, right? So S will be given at the root node. So we have covered three conditions here. If all training examples are positive, then make the root node as just positive. If all the training examples are negative, no further classification is required, right? So it can't learn anything. Machine can't learn anything. In that case, the root node will be negative. Now, if no attributes are given, only the target labels are given. What best can the machine learn? It can be in favor of the most repeated value, right? What is the most repeated value here? Yes. So that will be taken as the root node, right? All the extreme conditions are met. We covered with the algorithm. Now let us see if the training examples are having equal number of positive and negative classes. Equal number of training examples with yes and no. Then what we have to do? That is the actual case. That is where the machine has to learn in order to predict well with the future data points or unseen data. So what it has to, how it has to start with? Otherwise, means if any of these three conditions are not correct, then what further action has to take place? Begin. Into A, load the attribute from attributes that best classifies the examples. How it best classifies the examples? The measure called entropy we are going to see in the next, we are going to see further in the session. Entropy. We have some measures. We have some statistical measures in order to say whether a particular attribute used at the root node, married, marital status, or gender, or whether he owns a house, or his income level, which attribute better classifies the training examples. That has to be taken at the root node, right? Now, how to select that best classifier is by using a measure called as entropy. Okay, that I'll explain how it can be measured, but understand that the initial root node should be fed with the attribute which better classifies the training examples. Okay, that is what we are writing here. What should be the classifier A here? Classifying attribute here, the attribute from attribute set that best classifies the examples, that best classifies the given training examples. Okay, now what is the next step? The decision attribute for root should be A itself. Take an attribute which best classifies the training examples and make it as the root node. Okay, so you are taking a root node initially, finding which is the best classifier and putting it here, which is the best classifying attribute and putting it in the root node. That is how we start. I'll add at this end. See here. Root node starts with the attribute A, which better classifies the training examples. Now, for each possible value Vi of A, now assume A is income level of a customer. Okay. Now, this income level has three values: lesser than 5,000, greater than 10,000, greater than lesser than 10,000, lesser than no, or we'll do it like this: greater than 10,000, greater than 20,000, and greater than 30,000. We'll give a range: greater than 10,000 or less than 20,000, greater than 20,000, less than 30,000, and greater than 30,000 will be the third category. We have three different categories. We have three different ranges for this income level. So it has to proceed with those branches, right? For each possible value Vi, here Vi, we have three values of income level A, that is taken as A. Now, for this, add a new tree branch below the root. I added already this branch, and this branch, corresponding to the test A equal to Vi. Income equal to greater than 10,000, less than 20,000. That is this branch 1. Income equal to greater than 20,000, less than 30,000. That is my second branch 2. Income is greater than 30,000. That is my third branch 3. I have 3 branches here because there are 3 possible values for the income level, right? Okay, so these are the 3 possible category values for this income level A, this attribute what we have taken. Now let examples SVI. What do we mean by this SVI? S is the set of training examples and SVI is wherever the training examples income value is our first category or second category or third category. I am repeating again, listen carefully. S is the set of training examples and VI is the possible values for the attribute A. So the possible values is greater than 10,000, greater than 20,000, greater than 30,000, right? Now you are taking that value. Let example SVI be the subset of examples that have the value VI for A. So you're considering all the training examples where income value is this greater than 10,000, greater than 20,000 and greater than 30,000. All those values you are considering on each branch. Now if examples SVI is empty, now for this particular category there are no training examples given. Then what has to be done? Then below this new branch, add a leaf node. Directly you can add a leaf node with label equal to most common value of target attribute in examples. Okay. Now for income greater than 10,000, there are some extra conditions to be checked. For income greater than 20,000, there are some extra conditions to be checked. For income greater than 30,000, it is clearly seen from the training examples that the customer is a good payer of the loan. He will pay the loan. In that case, what you can do, you can make it as a leaf node. You need not further construct a subtree. You can directly make it as a leaf node. Now, here if there is another condition to be checked, here there is another condition to be checked. The tree will further grow to the next level. Okay, so that is what is mentioned in these 2 steps. If examples SVI is empty, in that case, below this new branch, add a leaf node directly with label equal to most common value of target attribute in the examples. Else, if that is not the leaf node, for the other cases of 1 and 2, what will happen? Else, below this new branch, add the subtree. Grow the tree to further levels, to next level. And again, it will apply this ID3 algorithm with the same approach. What is the approach now? Remaining examples, remaining training examples, the target attributes, and the attributes other than A. Look here, this is very important. One attribute we have already considered at the root node. Now that attribute is no longer available for further checking the classification. That is why when you pass in the second iteration the attributes to ID3 algorithm, you have to remove that A which is considered at this root node, right? So we should remove income criteria and check the training examples with other criteria, right? That is how this ID3 algorithm works. Then finally end and return the root node from where the entire decision tree can be tracked easily. Okay, this is how a decision tree is constructed. It finds the best classifying attribute, then it goes towards the descendants and finally checks each and every training example if a particular training example is better classified, then it ends there. If it is not classified purely, then it has to go with other further conditions to be checked. Now, let us see what is the approach to find out which is the best classifier, which attribute is the best classifier, right? So the central choice in ID3 algorithm is to select which attribute to test at each node in the tree. Now, start with the root node, which is the best classifier, which gives the better split of the training examples. Then you go for the next level, which is the best attribute at this stage in order to classify, to reduce the impurity in the classification. Okay, this is how the classification process goes iteratively in order to build the decision tree. Now, our choice is the attribute that is most useful for classifying the examples, that is very efficient in classifying the examples, that better classifies the training examples, right? So what is a good quantitative measure? What measure do we select which is worth of a quantitative measure of the worth of an attribute in order to find the capability of an attribute in order to result in pure classifications? What is the quantitative measure? The measure we take here is the information gain. We will define a statistical property called the information gain that measures how well a given attribute separates the training examples according to their target classification, right? So let us understand this information gain while understanding another concept called as entropy. Okay, these go hand in hand. When the entropy is less, information gain will be more. When the entropy is more, information gain will be less. So what is entropy? It is uncertainty in the classification. If the classification is uncertain, uncertain means not very confident. Okay, it has some impurity. When the attribute is not able to classify the training examples properly, okay, properly in the sense it has to classify them into their respective classes. If that is not happening clearly, if it is uncertain, in that case entropy value will be high, means information gain at that particular attribute will be low, means that attribute is not having much information gain. Because of considering that attribute, better classification is not being obtained, right? In that case, we say information gain is very less and uncertainty is more, means entropy is more, right? All these terms will be seeing again. You need not worry if you don't understand in the first instance. Now, entropy measures for homogeneity of examples. Homogeneity of examples means belonging to the same class. Homogeneity, homogeneous classification. All training examples belonging to one class completely or to a different class, like that. Now, in order to define information gain precisely, we begin by defining a measure commonly used in information theory called entropy. Okay, now let us calculate this entropy and find out the information gain at each attribute or at each node in the decision tree. Now, how is this entropy calculated? Let us see. In order to define information gain precisely, we begin by defining a measure commonly used in information theory called as entropy that characterizes the purity or impurity of an arbitrary collection of examples. If it clearly classifies all the training examples as per the labels given, then it is called pure classification. But if it is not able to still classify properly, there is some ambiguity in the classification, then we call it as impure classification. Okay, now given us collection of training examples S containing positive and negative examples of some target concept, the entropy of S relative to this Boolean classification is, how it is calculated, minus P plus log 2 P plus minus P minus log 2 P minus. Very simple. Don't get scared seeing this log terminology and all. If I give you the example, you will feel it very simple. Say there are some training examples like this. Now total how many examples I have given? 9 examples, right? Among this, what is the proportion of positive classes? 1, 2, 3, 4, 5 and 6. Right? So what is the proportion of positive class here? Minus proportion is 6 out of 9. Right? The proportion of positive classes in the training examples given is 6 out of 9. Log 6 by 9 minus what is the proportion of negative examples? 1, 2 and 3. So you have 3 out of 9 examples as negative examples or no classes, right? So it is 3 by 9 log 3 by 9. That's all. That is how entropy is calculated. After classification, it will check how many of the examples are positive and negative. It will count their proportion and use this formula in order to find the entropy of the tree, of the entire tree, right? Now let me show you another example. And before that, let me make you more clear what are the log values for log 1 and log 0. If it is log 1, the value is 0. And if it is log 0, the value will go to infinity. Right? These are all minimal mathematics that you need to remember before going forward with this entropy concept. Now in all calculations involving entropy, we define 0 log 0 to be 0. Why? Because log 0 is what? Infinity. 0 into infinity, it becomes 0, right? Now to illustrate better, suppose S is a collection of 14 examples. Now consider set of training examples. S is a collection of how many examples here? 14 examples of some Boolean concept. Boolean concept means the target values are yes or no, or a fraudulent transaction, fraudulent, not fraudulent, or cancerous cell, cancerous, not cancerous. Okay, these are all called as Boolean concepts, means the possible values are only 2 in the target label, right? In that case, we call it as a Boolean concept. Now, let us take 14 such training examples, including 9 positive examples, means the label of 9 training examples is yes, and 5 negative examples, means the training examples have the label no, right? Then the entropy of S relative to this Boolean classification is, can anybody quickly calculate and tell what is the proportion of positive examples? 9 out of 14. Apply the log 9 out of 14 minus what is the proportion of negative examples? 5 out of 14. Here it is 5, right? Out of 14 examples, 5 are negative classes. 5 by 14 log of 5 by 14. You can take your calculator and find out that value will be 0.940. That we are calculating as the entropy of this yes, means the set of training examples. Now what did you understand from the value of this entropy? 0.940. Is it high or low? Remember, entropy value lies between 0 and 1. Now you give me the answer whether this entropy value is high or low. You're there, students. This entropy value is high or low? It is very high. Why is it high? Out of 14 examples, 9 are positive examples and 5 are negative examples, right? Means they are not equal number of training examples given for positive and negative. If I'll give you a condition, if there are 7 positive examples and 7 negative examples, in that case the entropy will be 1. Listen carefully. If there are equal number of positive and negative examples in a training example set, then the entropy will be 1. How is that? We apply it as minus 14 by 14 log 14 by 14, because we have all positive examples. In that case it is 14 by 14, or all negative examples. In that case again it is 14 by 14. Now log 14 by 14 is nothing but log 1. Log 1 is what? This entire thing will be 0. 0 into whatever you give will be 0. Right? So whenever you have training examples with only one single class, all positive or all negative, in that case the entropy will be 0. There will not be any uncertainty in learning from those training examples, because all are yes only. So whatever you give further also, the machine predicts it as yes itself. So it predicts with 100% confidence. There is no uncertainty in its predictions, as the entropy is 0. Got it? Now, if there are equal number of training examples, 7 positive classes and 7 negative classes, in that case, the entropy will be 0.5. Means what it is having? It is having chances of predicting 50% as positive class and 50% of as negative class if a new data is given, if unseen data is given, right? So there is 50% uncertainty in the prediction. Then we say entropy is 0.5. Got it? That is how the entropy value will vary. That I'll show you in the picture. You will clearly understand. Notice that entropy is 0. That is what I explained right now. If all members of S belong to the same class. And also notice that entropy is 1 when the collection contains an equal number of positive and negative examples. Equal number of positive and negative examples. Yeah. Correct. I have given it as 0.5, I think. No. Sorry. It is not 0.5. It is 1. Why? Because we give it like this. Say 7 by 7. Log 7 by 7. 7 by 14. I'm very sorry. Yeah. This is how we give the examples. Minus 7 by 14. Log 7 by 14. Again, we have a minus 7 by 14 log 7 by 14, right? If you have equal number of classes, in that case, you can just take this value common, and that will result in 1. Okay, so when the collection contains equal number of positive and negative classes, in that case, this will be 1. If the collection contains unequal numbers of positive and negative classes, then the entropy lies between 0 and 1. Right? Say if there are 3 positive classes and 11 negative classes, or 9 positive classes and 5 negative classes. In that case, the entropy varies between 0 and 1. Right? Okay. Yeah. So here we can see that the entropy is 0.940. It is almost near to 1, which indicates that there is lot of imbalance in the number of classes. 9 classes are positive and 5 classes are negative. Got it? So this is the picture which shows how the entropy value varies. Initially, when all the values belong to a same class, Okay, all the values belong to a positive class, or all the training examples belong to a negative class. In that case, the entropy will be 0. Now, as the number of classes becomes equal, 50-50, say there are 7 positive classes and 7 negative classes. Out of 14 training examples, there are 7 positive classes and 7 negative classes. 50% of positive classes and 50% of negative classes. Then the entropy will be highest because there is uncertainty. Yeah, what I meant 0.5 is 50% of the training examples, right? 50% of the training examples are positive and 50% of the training examples are negative. In that case, the entropy will be very high because the uncertainty in prediction will increase a lot from the decision tree. It may predict it as 50% positive class or 50% negative class. In that case, the entropy will be 1, very high. Now, again, as it goes on, where the number of training examples belonging to a negative class are more and number of examples belonging to a positive class are less, in that case again the entropy will start coming down. Means if all the examples belong to a positive class or all the examples belong to a negative class, in that case the entropy is 0. Did you see this y-axis? The entropy is 0. But whenever there are equal number of positive and negative classes, then the entropy will be high, that is 1. Okay, so for multi-class classification, how you do this? We have seen so far for binary classification, that is when you have only 2 classes, yes or no. In that case, we can calculate the entropy as given by the entropy example. Proportion of positive classes and proportion of negative classes. Take their log values and keep them added. Now, if there are multiple classes, say I is from 1 to C. Normally in binary classification you have I equal to 1 to 2 because you have only 2 classes. But if you have C number of classes, say product is having defect 1, defect 2, defect 3, or it is working normal. In this case, we have 4 different classes. We have to classify into 4 different classes. In that case, how to calculate the entropy? It is nothing but the addition of all the individual terms. Say there are 4 classes, and for the first class it is 4 by 11, and for the second class it is 2 by 11, and in the third class it is 3 by 11, and in the fourth it is 5 by 11. So total we have 9, 10, 11, 14, right? If it is a binary classification with 14 training examples, we calculate as 2 different terms. But when you have multiple classification, then defect 1, defect 2, defect 3 are 3 different classes with normal as the 4th class. In that case, say if the training examples for defect 1 are given as 4 and defect 2 are given as 2, training examples for defect 3 is 3 and normal functioning of that product is 5. In that case, we can have the proportion as 4 by 11, 2 by 11, 3 by 11 and 5 by 11. Now how to calculate the entropy of this? Minus 4 by 11 log 4 by 11 minus 2 by 11 log 2 by 11 and so on. Minus 3 by 11 log 3 by 11 minus 5 by 11 log 5 by 11. That is mathematically represented as a sigma function. Sigma means what? Summation. You are summing up all the values and giving a generic representation like this. Pi. Pi is the proportion of the training examples with that particular class I. Right? Pi is the number of training examples, proportion of training examples that belongs to class I. Right? So that can be calculated by using this formula. just we have seen for binary classification, and we have generalized it to multiple class classification. If there are C number of classes, then this will be the formula to calculate. Now, given entropy as a measure of the impurity in a collection of training examples, we can now define a measure of the effectiveness of an attribute. We know that entropy will measure the purity or impurity in classification. If that is able to be calculated, then we can also calculate the effectiveness of an attribute in making that classification. That is called as the information gain. When we are measuring the purity in the classification with entropy, the effectiveness of making that classification by an attribute, that is measured as the information gain. What information gain is obtained at attribute A? What information gain is obtained at attribute A2? What information gain is obtained at attribute A3? When they are used as the root nodes for checking the condition, right? That has to be seen. It is simply the expected reduction in the entropy. I said already, information entropy is more means information gain is less because of that attribute. Entropy is less means information gain because of that attribute is more, right? That is how you need to understand. Now the information gain, how do we mathematically represent this information gain of an attribute A is relative to a collection of examples S is defined as gain S of A. Understand this representation. Information gain in the training examples S by using the attribute A is equivalent to, how do you calculate that? Entropy of the whole set of training examples and entropy for that particular attribute. See, V belongs to values of A, categories of A. Now, when you take the training examples with that particular value for that attribute A, what is the entropy? Okay, that is calculated, and the difference between the overall entropy minus the entropy with that particular attribute will give you the information gain. I'm repeating again, calculate the entropy for the overall training set, overall training examples. Now calculate the entropy for a particular attribute, means using that attribute, how better is the classification done? How pure is the classification? Or what is the impurity in the classification, right? Say you're taking an attribute A. Now, with that attribute A itself, you are able to classify all the training examples properly. In that case, we can say that its entropy is 0, right? Then we say that this is most efficient attribute. It is perfectly classifying all the training examples by checking only on that attribute. Then we say that the information gain at this attribute is more. Okay, because the entropy is 0, very less. Okay. That is what we are giving with this formula, where values of A is the set of all possible values for attribute A, and SV is the set of S for which the attribute A has value V. Say A is sunny. What are the values for that? What is the value set for sunny, rainy, sky? I'm extremely sorry. A is the attribute value, attribute name sky. A is the attribute name sky. Now, what are the set of values allowed for this attribute? That this is A. Now we are writing the value set for that attribute: sunny, rainy, and cloudy. This is the value set V. Now, how you are calculating the entropy? Wherever the training example have that value sunny or rainy or cloudy, divided by the total number of training examples, that gives the proportion of that particular value, right? Multiplied by the entropy at that attribute. Okay, the difference between these two will give you the information gain at a particular attribute. So in order to increase the information gain, this entropy should be less. Got it? whenever this entropy is less, the right hand side value is less, the left hand side value will increase, right? This is less and this is less, this overall value will be less. That will increase the information gain. Means reduction in the entropy will increase the information gain. Increase in the entropy will reduce the information gain at a particular attribute A. Okay, this is all preliminary explanation I am giving you. With an example, you will clearly understand, do not worry. So gain S of A is thereof the expected reduction in entropy caused by knowing the value of attribute A. Now put another way, if you want to define it in another way, gain SA is the information provided about the target function value given the value of some other attribute A, right? This is how we need to understand about information gain and entropy. Once we go through the example in the next class, it will be very clear for you how to calculate the entropy. And this is the compulsory question in your exam. Calculating the entropy and information gain will be a problem that, that can be given to you in the exam. You have to calculate what is the entropy and what is the information gain, and accordingly build a decision tree when some training set is given to you. Okay, so listen this carefully. In next class with an example, I'll explain all these concepts once again so that you'll clearly understand about that. Now quickly answer my questions. What does entropy suggest about classification? What does entropy measure suggest about classification? Any answer from your understanding? I don't expect it to be completely correct. What you understood. Based on that, I can refine my explanation in the next class. What is entropy? What does entropy suggest about classification of training examples? Students? I need to end the class, right? Speak out something. What does entropy suggest? It suggests about purity or impurity in the classification, certainty or uncertainty in the classification, right? What is the opposite of entropy? Anybody? What is the opposite of entropy? Larger is the entropy, what will be lesser? Lesser is the entropy, what will be more? What should I understand if none of you are speaking? Speak out. What is the opposite of entropy? Not in the literal sense. The measure I'm asking you. Information gain, right? Larger is the information gain, lesser is the entropy. Larger is the entropy, lesser is the information gain. Now give an example of pure classification or impure classification. What is pure classification? If an attribute can classify the training examples into equal number of positive and negative classes, there is no impurity in the classification, right? But if there is some imbalance between the classes, classification between the classes, then we call it as impure classification, right? All these terms once again will be going, we'll understand it better by going through an example. Any doubts, students? Till here? See, 27 students are there in the class. Nobody is answering.
No doubt.
Okay. But still, if there is any less understanding about this concept, surely it can be understood in the next class. Be present for the next class. This is very important concept, and compulsory question will be given in the exam on this. You have to calculate entropy and the information gain for the training example set given while constructing a decision tree. Okay? Okay. We'll meet in the next class.